Okay, today we are discussing about starting the third module, subroutines and control abstraction. And this module consists of static and dynamic links, calling sequences, parameter passing, generic subroutines and modules, exception handling, coroutines. These are the topics in third module. And today we are focusing on static and dynamic links and calling sequences. First of all, we are discussing about abstraction and subroutines. Abstraction can be defined as a process by which the programmer can associate a name with a potentially complicated program segment. Here, the focus is on the purpose or function rather than its implementation. Mainly, the abstraction means displaying only the essential information and hiding all the details. That is, preserving the information that is relevant in a given context and neglecting all the irrelevant information in that context. This is all about abstraction, and we can distinguish abstraction as control abstraction and data abstraction. The control abstraction is the abstraction in which the principal purpose is to perform a well-defined operation. That is, here it hides the implementation details. That is, the control abstraction mainly focus on hiding the implementation details, and data abstraction focus on representation. That is, it giving importance to the representation. So it hides the details about the data. Subroutines perform its operation on behalf of a caller. So subroutines are the principal mechanism for control abstractions in most programming languages, and the caller calls a subroutine, and most subroutines are parameterized. The caller passes the arguments that influence the subroutine's behavior, or we can say that the caller provides subroutines the data on which to operate. That particular arguments are called actual parameters, and these actual parameters are mapped to a subroutine's formal parameters at the time a call occurs. A subroutine that returns a value is usually called a function, and a subroutine that doesn't return a value is called a procedure. In some languages, the functions and subroutines are treated in the same sense, and most languages require subroutines to be declared before they are used. But a few languages such as C, Fortran, Lisp, etc. doesn't require the early declaration. The declaration allows the compiler to check whether is it calling the right subroutine, or whether it is passing the right number of arguments, or whether it is passes the right type of arguments, etc. That is, the declaration allows the compiler to verify that every call to a subroutine is consistent with declaration. In most languages, the storage consumed by the parameters and local variables can be allocated on a stack. So we are just reviewing the stack layout. Each subroutine, as it is called, is given a new stack frame or activation record at the top of the stack. The frame contains arguments, return values, bookkeeping information including return address and saved registers, local variables or temporaries, etc. And on returning from the subroutine, its frame is popped from the stack. The stack pointer register contains the address of either the last used location of the top of the stack or the first unused location, depending on particular convention. The frame pointer register contains an address within the frame. The objects in the frame are accessed via displacement addressing with respect to the frame pointer, and if the size of an object is not known at the compile time, then the object is placed in a variable sized area at the top of the frame. then its address and the dop vectors are stored in the fixed portion of the frame at a statically non-offset from the frame point. The dop vector includes it is a data structure that contains the variables or arguments at a runtime. If there is no variable size objects, then every object within the frame has a statically non-offset from the stack point. Then in a language with nested subroutines and static scoping, the objects that lie in the surrounding subroutine can be found by maintaining a static chain. There, each stack frame contains a reference called a static link to the frame of the lexically surrounding subroutine. That is, each stack frame contains a reference to the frame of the lexically surrounding subroutine, and this reference is called static link. The saved value of a frame pointer which will be restored on subroutine return is called dynamic link. The static and dynamic links may or may not be same depending on whether the current subroutine was called by its lexically surrounding subroutine or by some other subroutine nested in the particular surrounding subroutine, etc. Then in the figure, the calling sequence is A, E, B, D and C. The subroutines A, B, C, D are nested as shown on the left. The code for subroutine C can find the local objects at non-offset from the frame pointer. Then it can find local objects of surrounding scope B by dereferencing its static chain once and then applying the offset, that is displacement addressing. Then it can find the local objects of B's surrounding scope, that is A, by dereferencing its static chain twice and then applying an offset. Then if a subroutine D is called directly from B, then it is not visible in A or E because it is nested inside B. So it will not be visible on A and E. Here within B, C and D, all 5 subroutines are visible, and within A and E, the routines A, B and E are only visible, but C and D are not visible here. Next is calling sequence. Maintenance of a subroutine call stack is the responsibility of calling sequence, the prologue and epilogue. The calling sequence is the code that executed by the caller immediately before and after the subroutine call, and the prologue is the code executed at the beginning of the subroutine, and the epilogue is the code executed at the end of the subroutine. Sometimes this calling sequence is used to refer to the combined operation of the caller, the prologue and the epilogue. Before subroutine can be executed, first a subroutine frame is created. Then the tasks that must be accomplished on the way to into a subroutine include passing parameters, saving the return address, changing the program counter, changing the stack pointer to allocate space, then saving registers including the frame pointer that may contain important values that may be overwritten by the callee and all, and changing the frame pointer to refer to the new frame, and executing initialization code for any objects in the new frame that require it. These are the informations on the way to a subroutine. And after the subroutine code is executed, we have to remove the particular subroutine frame. So the tasks that must be accomplished on the way out include passing return parameters or function values, executing finalization code or any local objects that require it, then deallocating the stack frame, that is restoring the stack pointer, restoring other served registers including frame pointer, and restoring the program counter. Some of these tasks, etc., for example, passing parameters and all must be performed by the caller because they differ from call to call. And most of the tasks, however, can be performed either by the caller or the callee. In general, the space can be served if the callee does as much work as possible, because the task performed the callee appears only once in the target program, but the task performed in the caller appears at every call site, and typically a subroutine is called more than once. Next is saving and restoring registers. The ideal approach is to save precisely those registers that are both in use in the caller and in needed for the other purposes in the callee. Because of separate compilation, it's difficult to determine the intersecting set, that is the registers needed for caller and callee. And a simple solution is that for caller, save all registers that are in use, and for the callee, save all registers that it will overwrite. And a compromised solution is that registers not reserved for special purpose are divided into two sets of approximately equal size. One set is for caller's responsibility and the other is for callee's responsibility. Then the compiler uses the callee serves register for, compiler can use the callee saved register for local variables and other long lived values whenever possible, and it can use the caller saved register, that is caller saves register for transient values which are less likely to be needed across the calls. So the caller saved registers are seldom saved by the either party, that is the callee knows that they are the caller's responsibility and the caller knows that they don't contain anything important. So this reduces storage space. Maintaining the static chain. In a language with nested subroutines, the work required to maintain the static chain must be performed by the caller rather than by the callee, because this work depends on the lexical nesting depth on the caller. The standard approach is for the caller to compute the callee static length and pass it an extra hidden parameter. Two subcases arises here. First one is the callee is nested directly inside the caller. In this case, the callee static link should refer to the caller's frame. The caller therefore passes its own frame pointer as the callee static link. That is the first case, that the callee is nested directly inside the caller. Then the callee static link should refer to the caller's frame. That is so therefore the caller passes its own frame pointer as the callee's static link. The second case is that the callee is k greater than 0 scopes outward, that is that much closer to the outer level of the lexical nesting. In this case, all scopes that surround the callee also surround the caller. That is in that case, otherwise the callee will not be visible to the caller. So the caller dereferences its own static link k times and then passes the result as the callee static link. Then a typical calling sequence. The figure shows one plausible layout of a stack frame. The stack pointer SP points to the first unused location on the stack or the last used location depending on the compiler and machine, and the frame pointer FP points to the location near the bottom of a frame. The space for all arguments is reserved in the stack even if the compiler passes some of them in registers. The arguments are accessed at positive offset from the frame pointer FB, and the local variables and temporaries are accessed at negative offset from FP, and the arguments to be passed to the called routines are assembled at the top of the frame using positive offset from the stack pointer. To maintain the stack layout, the calling sequence might operate as follows. The caller saves any caller saves registers whose values will be needed after the call, then computes the values of arguments and move them into the stack or registers, then computes the static link. That is, if this is a language with nested subroutine, then it computes the static link and passes it as an extra hidden argument. And the caller uses a special subroutine call instruction to jump to the subroutine and simultaneously passing the return address on the stack or in the register. In its prologue, the callee allocates a frame by subtracting an appropriate constant from the stack pointer, and it serves the old pointer into the stack and assigns it an appropriate new value, and saves any callee saves registers that may be overwritten by the current routine, including the static link and return address if they were passed in the registers. Then after the subroutine has completed, the epilogue moves the return value, if there are any, into a register or a reserved location in the stack, and it restores the callee saves registers if needed, and it restores the frame pointer and the stack pointer, and the epilogue jumps back to the return address. Then finally, the caller moves the return value to wherever it is needed and restores the caller saves registers if needed. These are the sequences in calling a subroutine done by the caller, epilogue, prologue and the caller. And next is special case of optimizations. Many parts of the calling sequence, prologue and epilogue can be omitted in common cases. If the hardware passes the return address in a register, then the leave subroutine can simply leave it there. It does not need to save it in the stack. A leave subroutine means a subroutine that makes no additional calls before returning. That subroutine is called a leave subroutine. So, if the hardware passes the return address in the register, then the leave subroutine can simply leave it. That is, it does not need to save it in the stack. And also, it need not have to save the static link or any caller saves registers. A subroutine with no local values and nothing to save or restore may not even need a stack frame on the disk machine. And next optimization is that the simpler subroutines may not touch memory at all except for fetching instructions. That is, they may take their arguments in registers, compute them entirely in caller saves registers, and call no other routines and return their results in registers, etc. Then the simpler subroutines may be extremely fast. And simpler subroutines means, for example, library routines to compute standard mathematical functions, etc. These functions are called simpler subroutines. Next is displays. This is also an optimization technique. So, one disorder of static chain is that access to an object in a scope k levels out require that the static chain can be dereferenced k times. If a local object can be loaded into a register with single memory access, that is with single displacement mode memory access, then an object k levels out will require k plus 1 memory access. That is, an object k level out require a k plus 1 memory access. So, this number can be reduced to a constant by using display. A display is a small array that replaces a static chain. In display, the jth, it's an array, so the jth element of a display contains a reference to the frame of the most recently active subroutine at lexical nesting level j. If the currently active routine is nested I greater than 3 levels deep, then the elements I minus 1, I minus 2 and I minus 3 of display contains the values that would have been the first 3 links of the static chain. Then an object k levels out can be found at a statically non-offset from the address stored in the element j as I minus k of the display. The cost of maintaining a display in the subroutine calling sequence is slightly higher than that of maintaining a static chain, but the cost of dereferencing the static chain can be reduced by caching the links in registers when appropriate. However, the cost is less, but displays are less common today as subroutine nesting is mostly not allowed in all languages. Next is register windows. An alternative way to save and restoring registers on subroutine calls and returns is a hardware mechanism that's known as register windows. The basic idea here is to map the instruction set architecture, ISA, that is instruction set architecture's limited set of register names onto some subset of a much larger collection of physical registers and to change the mapping when making subroutine calls. Then setting and resetting a mapping is cheaper than saving and restoring registers. And also a new and old mapping registers overlaps to allow the parameter passing. And commercial processors like Sun Spark, Intel IA64, that is Titanium, it uses this register windows. Next is inline expansion. An alternative to stock-based calling conventions is an inline expansion. Many language implementations allow certain subroutines to be expanded inline at a point of call. And in inline expansion, a copy of the called routines becomes part of the caller. That is, in inline expansion, a copy of the called routine becomes a part of the caller. The inline expansion avoids a variety of overheads such as including space allocation, branch delays from the call and return, maintaining the static chain or display, and often saving and restoring registers. It also allows the compiler to perform code improvements such as global register allocation, instruction scheduling, common sub-expression elimination across boundaries between the subroutines, etc. In many implementations, the compiler chooses which subroutine to expand inline and which to compile conventionally. In some languages, the programmer can suggest that particular routines be inlined. In C++ and C99, the keyword inline can be prefixed to a function declaration. That is inline, for example, inline int max of int a, int b, then return a greater than b, then question mark a, that is it's a ternary operator. So the keyword inline allows to, the inline can be used by a programmer here. So in comparison to the real subroutine calls, the inline expansion has an obvious disadvantage of increasing code size. since the entire body of the subroutine appears at every call site because it is inlined in the particular code. So, entire body of the subroutine appears at every call site. In inline expansion is also not an option in general case of recursive subroutines. So, inline expansion cannot be used in recursive subroutine also. So, this is all of today's class.